Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am from Department of Computer Science, Aryabhat College, University of Delhi. Today's topic is Strassen matrix multiplication. So the term matrix multiplication, when I talk about this term, the first thing which comes in our mind is about the two matrices, and here is a multiplication going on in between them. So that's the problem, that's the agenda for today's lecture. So when we talk about basic matrix multiplication, suppose we want to multiply two matrices and the size is n cross n, and let us say we have two matrices A and B, and let us say we have our product, their product as C. So in this I am taking an example of 2 cross 2. So A11, A12, A21, A22 when multiplied by B11, B12, B21 and B22 is going to give us the resultant matrix as 2 cross 2, and here we have that resultant matrix as C11, C12, C21 and C22. And when we talk about this basic matrix multiplication, so we have C11 as the sum of A11 multiplied by B11 and A12 multiplied by B21, and this is the kind of formula which goes on. So this 2 cross 2 matrix multiplication can be accomplished in 8 multiplications or 8 scalar multiplications, if we say. So this is what our basic matrix multiplication algorithm is. So here we have 2 loops in order to compute Cij, and in order to compute this Cij we need to have a third loop. So Cij is going to be sum of I is equals to 1 to n, Aik and Bkj. So essentially if we analyze the time of this basic matrix multiplication, or I can say that if we are going to elaborate this method, this function of basic matrix multiplication, we will be having 3 loops here, and the time analysis or the time complexity results in order of n cube. So basic matrix multiplication is actually we can say is a costly, although it is a polynomial time algorithm, but is still being an order n cube algorithm, it is a costly algorithm. So here we consider row I of the matrix A and the column j of B, multiplied together the first entries of the row and column, the second entries, and then so on and so forth. Add up all the products, and here we are going to get the ijth entry of the matrix C. This is the basic procedure of our naive matrix multiplication if we talk about. So number of scalar operations, which is multiplications and additions, is very straightforward, and that comes to order n cube if we compute the time complexity. Now a similar question, or the question which haunts algorithm designers forever, is can we do better than this? Can we do faster than this? So yes, the answer is yes. Here comes in the picture the divide and conquer algorithm, or divide and conquer technique to be precise. So divide and conquer, let us revise this divide and conquer technique first, and then we will see how this divide and conquer can be a savior in terms of or an application of matrix multiplication. So divide and conquer, basically a general algorithm design paradigm, and I am sure you all are aware of this. This is a very simple simple technique which is applied to merge sort and various other algorithms, various other applications. So this is having 3 steps. Basically one is divide. So divide says we need to divide the input data. Let us say the input data is S in disjoint subset. There can be 2 disjoint subset, or there can be more disjoint subset. So that input data S is to be divided into S1, S2, S3 and so on and so forth. Then the next step is recur, which says solve these sub problems recursively. And the final step is to conquer. To conquer is to combine the solution for this S1, S2, S3 these sub problems, and finally get a solution for your the general problem or your bigger problem which is defined as S. So, this is a simple divide and conquer algorithm, and if we talk about the recursion or implementing this divide and conquer through recursions. So, the base case for recursion is actually the sub problem of the constant size and which cannot be divided further. So, for example, if I am talking about the base case of the merge sort, it is the array of size 1, which is obviously a constant size, and the analysis of this divide and conquer approach can be done using recurrence equations. So, how are we going to use this divide and conquer algorithm for a matrix multiplication? So, better than the naive approach, we have a slightly better approach which is based on this divide and conquer. So, it is also an order n cube time algorithm, and space it is taking as order n square. So, here the idea is to divide the given matrix into 4 sub matrix of order n by 2 multiplied by n by 2, and then calculate the values AE plus BG, AF plus BH, CF plus DH as shown in the image. Here if you can see, A and B are the matrices, square matrices to be precise, of size n cross n. We are going to apply this approach on the square matrices. So, A and B are the square matrices, so C is also a square matrix. Then A, B, C and D are the sub matrices of A, and if you calculate the sub matrix size, this is going to be n by 2 cross n by 2. Similarly, your E, F, G, H are also the sub matrices of size n by 2 cross n by 2, and these are the sub matrices of B. And if we are going to multiply, so we have AE plus BG, which is going to form the first cell or the first matrix, first value of the matrix C. Then for second value we have AF plus BH. For the third value, which is in the first, which is the first value of the second row, this is CE plus DG, and then for the last value, this is CF plus DH. So, we can have a divide and conquer approach which is going to be a better approach in this way. But if we apply the Strassen matrix multiplication, Strassen showed that in order to multiply a 2 cross 2 matrix which can be accomplished in 7 multiplications and 18 additions or subtractions, and this reduce can be done by divide and conquer approach. So, number of multiplications and number of additions, this is what Strassen is going to kind of, we can say, hit, and this is what he is trying to, or he was trying to reduce. So, if we talk about divide and conquer matrix multiplication, so here is the kind of, we can say, we have matrices A and B, and the resultant matrices is also shown here. We are going to divide the matrices into sub matrices A0, A1, A2, A3 and B as B0, B1, B2, B3, and we use blocked matrix multiply equations and then recursively multiply the sub matrices. So, this is what we can say is the basic bottom line of divide and conquer matrix multiplication if we are going to do this. So, in case of a 2 cross 2 matrix, this is going to be A0 is going to be one element, but if we go on for higher matrices, this is going to give us the matrices of size n by 2 each. So, that is what where your actually this Strassen matrix multiplication is going to give you lower time complexity, and how what kind of lower time complexity I am talking about, that I will show at the end of the lecture. and so this is basically a recursion, because we are, in order to multiply a large matrix, we are dividing it into n by 2 cross n by 2 matrices, and then we are kind of multiplying it. So, this can be very simply we can say achieved with the help of recursion. And recursion, if we talk about, we always need a base case to terminate the recursion. So, in order to terminate the recursion, we have a simple base case here, where your A and B are nothing but the single elements, which are A0 and B0, and the resultant matrix is obviously A0 multiplied by B0. So, this is going to be we can say a simple base case in order to terminate the recursion. Now, what is the strategy of Strassen, or we can say what is the formula of Strassen? So, here if you can see on the screen, in order to multiply two matrices A and B, which are going to have a resultant matrix C, some 7 matrix multiplications and 18 subtraction and addition, if you count in all these equations, that is what the precise number is. So, here your P1, P2, P3, P4, P5, P6 and P7 we can say are the intermediate, some intermediate results which are calculated as shown in the formulas. So, P1 says A11 plus A22 multiplied by B11 plus B22. P2 says it is A21 plus A22 multiplied by B11. P3 says A11 multiplied by B12 minus B22. P4 is equals to A22 multiplied by B21 minus B11. P5 is equals to A11 plus A12 multiplied by B22. P6 is equals to A21 minus A11 multiplied by B11 plus B12, and P7 is equals to A12 minus A22 multiplied by B21 plus B22. After determining all these we can say intermediate values, which are P1, P2, P3, P4, P5, P6 and P7, we are going to determine the elements of our resultant matrix, which are nothing but C11, C12, C21 and C22. So, C11 here is P1 plus P4 minus P5 plus P7. C12 can be calculated by P3 plus P5. C21 is equals to P2 plus P4. C22 is equals to P1 plus P3 minus P2 plus P6. So, this is what I can say Strassen matrix multiplication method in a nutshell is, in which I am having all the intermediate results which are from P1 to P7, and how these results with P1 to P7 are being used in calculation of C11, C12, C21 and C22, which finally will make a complete resultant matrix C, is also shown in these formulas. Now, here is basically you can say a recursive function which is going to calculate this Strassen or which is going to implement this Strassen algorithm. So, we can have one matrix multiplication method in which we are going to pass the matrix A, matrix B, the resultant matrix R obviously, and of course, the size which is n, and the base case is if n is equals to 1. I have already told you about the base case, which is A0 into B0 is going to give us the resultant matrix R0, or if it is not the case, if if recursion is not in the base case presently, then you need to calculate all these matrix multiplication, all these 7 multiplications. So, basically the bottom line is we have divided the matrices into sub matrices, and we are recursively multiplying this sub matrices in order to fulfill this particular kind of we can say a formula sheet, or this particular in order to determine, in order to calculate, in order to find all these P1 to P7 values, which are further being used in the calculation of your final resultant matrix, which is nothing but C. So, we have seen the formula, we have seen kind of a short we can say a pseudocode also. Let us see an example. Here I have taken a simple example of 2 cross 2. So, A is having 1, 2, 3, 4 and B is 5, 6, 7, 8, and if I am going to divide this A and B each into kind of 4 sub matrices, the size will be 1 which is nothing but 1 cross 1, which is nothing but n by 2 into n by 2. So, so for matrix A, we have A11 as 1, A12 as 2, and this is all a very kind of a simple terminology. A21 is equals to 3, A22 is equals to 4, and similarly for matrix B, we have 5, 6, 7 and 8. Now, when we are going to apply Strassen matrix multiplication method on this, so here we have M1 to M7, or you can call them as P1 to P7. These are simple kind of variables we can say. So, M1 is A11 plus A22 multiplied by B11 plus B22 which is coming as 65. Then M2 applying the formula A21 plus A22 multiplied by B11, which is 3 plus 4 multiplied by 5, finally it is coming as 35. Then M3, the formula is A11 multiplied by B12 minus B22, which is 1 multiplied by 6 minus 8 equals to minus 2. Then we have M4 going by the formula of A22 multiplied by B21 minus B11, it is coming out as 8. Then we have M5, which is A11 plus A12 multiplied by B22, coming out to 24. M6 is A21 minus A11, the whole thing multiplied by B11 plus B12, which is 3 minus 1 multiplied by 5 plus 6, coming out to 22. And finally, M7, which is A12 minus A22 multiplied by B21 plus B22, and the result is minus 30. So, here we have all the intermediate values starting from M1 to M7, and now we are going to plug in these values into in order to compute each element of the resultant matrix C. And in order to plug in, the formula is C11 is equals to M1 plus M4 minus M5 plus M7. So, it is coming out to 19. C12 is equals to M3 plus M5, that is equals to minus 2 plus 24, result is 22. For C21, the result is 43, which is coming out by M2 plus M4, and C22 is M1 minus M2 plus M3 plus M6, which is coming out as 50. So, in calculation of these M1s and also in calculation of all these resultant elements of the matrix of the final result matrix C, if you calculate, there are precisely 7 matrix multiplications and 18 addition and subtractions, and finally, if you see here, C is equals to 19 and 22 in the first row and 43 and 50 in the second row, which is exactly kind of the same result which we obtained using the naive matrix multiplication. Now, if we talk about the analysis of time analysis, so when the problem is of size 1, that means T of 1 is equals to 1, and here we are assuming, the assumption is our n is equals to 2 to the power k, that means our size is we can say a multiple of it is in the power of 2. So, T of n is equals to 7 T n by 2. So, that means we are multiplying 7 matrices of n by 2 size each, applying this formula of T n is equals to 7 T n by 2 for n is equals to 2 to the power k, we get 7 to the power k T n upon 2 to the power k, and that is equals to 7 k. So, precisely if you can see, T n is coming to n to the power 2.81, and the previous, or in the naive matrix multiplication, the complexity was n to the power 3, and in divide and conquer, or in matrix, this Strassen matrix multiplications, we have reduced it to the n to the power 2.81. So, is it actually kind of, we can say, is it very relevant to get from or to reduce from n cube to n to the power 2.81? So, yes, we can say that for higher kind of for higher numbers, yes, it is very significant. So, here are some figures of running the different running the different sizes of n. So, when it is kind of n is 32, the iterative method is having kind of we can say complexity of or the time complexity, the time taken as 67 units. Recursive is having 78. Strassen here is giving bad results, 149. Then for 64, if we compare, it is coming out to lesser for Strassen as compared to iterative and recursive, and that too with a kind of figure of 40% less. If we talk about size of 128, it is coming as kind of close to 50% lesser, and for 256 it is also again an improvement of kind of huge improvement, we can say 40% or something. So, yes, implementing a Strassen algorithm for bigger sizes is actually an improvement which we can say from order of n cube to order of n to the power 2.81. But if we get into the discussions of a Strassen algorithm, is it always practical to use this? No, we cannot say that, because constant factor is larger than for the naive methods. There are specially designed methods which are better on sparse matrices. Strassen method is practically not very good with sparse matrices, and also recursion comes with its own cost, which is actually a lot of space. And Strassen again is not the fastest known method. The fastest known method is giving us a complexity of order n to the power 2.376. So, here in this lecture we have seen how this naive matrix multiplication works, and then we have the Strassen matrix multiplication. We have seen the formula, the results. Is it actually better to use this Strassen matrix multiplication? We have also seen an example of this, and we discussed that as when to use this Strassen matrix multiplication. So, this is all from my side for this particular lecture. I will see you in the next one. Till then, take care.